Yeah, hi. Thank you for giving me the opportunity to speak today. I feel like a little bit of an imposter because unlike most other people in this session, I don't actually look at black holes. I look at the things that pretend to be black holes. But very aptly, they're also imposters. So, we've got that in common at least. And today specifically, I want to talk about a detailed analysis of a sample of black hole impostoring post-mass transfer binaries, which is a mouthful, so we're just calling them imposters for this. And this is work that I undertook while I was still at MPI-A, but I thought today would be a good chance to talk about this. And what specifically the sample that I want to talk about was a sample that was first introduced or analyzed by Karim and Hans Walter. And when I talk about this paper, I'm going to be referring to it as Alberto Enriques or Alberto Enriques 22, just in case it comes up a whole bunch. And basically, the sample was selected from the Gaia DA3 catalog by looking for targets that were SP1s with high mass functions. And high mass function just means that we have a very massive secondary relative to the primary. And if we put 2 and 2 together, right, we've got SP1, so we can only see one signature of a spectrum. We believe that our secondary is heavier than our primary, and those two things together suggest that we're looking at dark companions. So Karim has also looked at this, and by fitting in the spectral energy distribution to observe photometry, actually found that none of these contain a dark companion, but in fact all consist of 2 bright components. And the way that you can tell that with SCDs is that you take the photometry in sort of different bands, and you try and fit an SCD to this. And if you cannot fit a single component SCD, because you either get excess in the red or in the blue, you then instead can go ahead and try and fit a 2-component SCD. And if that 2-component SCD gives you a very, very nice result that's significantly better than the single-component SCD, then that's a good hint for you that you may be looking at SP2 systems with 2 bright components rather than an SP1 system. In one of the targets, there was also archival spectral data, which would also be fit using spectra of the parameters that were implied by the SCDs. And what we think is happening here, and the way that these systems are fooling us, harking back to what Ilva was saying earlier about these stripped stars, is that these are systems where the more massive star has started evolving and has started filling its Roche lobe, transferring mass into the secondary. The secondary in the process spins up, and there's a lot of sort of weird physics going on that make us believe that the system is an SP1 system, whereas it is actually an SP2, just because of the inverted mass ratio. And by getting spectra, we can actually learn more about these systems. And many of them have been talked about in the past as a non-exhaustive list, but basically these post-mass transfer, puffed up primary, rapidly rotating, much heavier secondary are not unique. And we've got a sample here, non-exhaustive list, but if you're interested, here's more about them. So what do we actually want to do, and what do we want to learn about these systems? Well, one thing that's important to think about is if we can see emission in the spectra that we're taking, because that will tell us if there's some kind of disk that's still there, whether mass transfer is maybe still ongoing or has ceased very recently. We want to learn about the mass ratio, because that will let us understand the system better. We want to understand the rotation, because this is very important for angular momentum transport in binary mass transfer. We want to know about the light ratio, because this will give us a further constraint on the SCD fits, and we also want to learn more about their mass transfer history. And the way that we do this is via spectral disentangling, and luckily Kunal has talked a little bit about this, but I just want to drive home the point that in spectral disentangling, we're making the assumption that we have 2 spectra, they're time invariant, and they're just sort of red and blue shifted as the 2 components orbit each other. And the reason spectral disentangling is really good for these sorts of systems where we maybe have rapidly rotating stars, or we have strange lines, or maybe even have emission features, is that spectral disentangling is template agnostic. So I don't have to presuppose any physics that I think I know about the system, and rather just look at the sort of observe the composite spectrum over a couple of epochs, and then ask the question, what 2 spectra do I need to take, and sort of shift against each other. And these spectra can look strange due to rapid rotation, due to emission, etc. And there's an algorithm that I wrote up. Tomar obviously has the other one. There's lots of cool stuff to do with disentangling. So procedure-wise, we disentangle our spectra, and these disentangled spectra immediately let us see if we have some sort of emission feature going on in our Obama series. We then go forward and we try and fit templates to the individual decomposed spectra, and that will give us information about the stellar parameters, the temperature, surface gravity, and very importantly, the rotation rate. When we have done that, we use these templates to do a 2-dimensional cross-correlation using the Todcrow algorithm, and this, and so we'll show this in a moment, will give us the mass ratio of the 2 components, or an independent measure of the mass ratio, which will let us then assess the mass transfer history if we combine it with a period. And then we do disentangling over the whole spectral range. We split it into boxes, and for each box we try and fit the flux ratio, the light ratio, for this specific wavelength bin, which is kind of like a flux ratio as a function of the wavelength, but sort of piecewise. So thinking about emission and rotation, here's one of our targets that we've disentangled. On the top we see the observed spectrum, so the composite that has the 2 components in it. The middle two panels give us the donor and the accretor spectrum, and the bottom is just the residual. So if we take the disentangled spectra, shift them to the relevant frame, add them up, and then take the difference between the observation and the reconstruction, this is our residual. So if there's like big features in the residual, our disentangling hasn't worked. In this case, the residual looks just noisy, basically, which is fine. And what we can see immediately, if we look at these two components, is that in our accretor, this is the H-beta line, we see these nice emission rings on either side. So yes, there's emission in this target. It's the only target where it's such a clear case. With the other ones, it doesn't look like there's any emission, which really just means that the mass transfer probably ended a little bit longer ago. If we then move on to the MG2 region, we can use that to fit the rotational velocity of our secondary. And the reason we don't do that with the Bama series is because the Bama series is really bad for rotation. And what we see is that with our best fit templates, our donor velocity is moderate, but it's fairly small. It is consistent with tidal synchronization, whereas our accretor rotational velocity is very high. So we're looking at 150 to 200 kilometers a second for all of them, which importantly is large, so is sort of consistent with this picture of the accretor being spun up by the accretion and the angular momentum transfer, but it is much slower than critical rotation. In these systems, it's about half of the expected critical rotation. And this is strange to us because we expect actually a very small amount of mass transfer to be able to speed us up to critical, but we haven't. So this is sort of an ongoing puzzle. Looking forward to the mass ratio, we have our templates, we do the 2D cross correlation, we get our velocities of our primary and our secondary, and we can plot them against each other. We do this in different wavelength windows to sort of remove any systematic effects that we get. And by fitting a straight line to these velocities, we can then get estimates of the mass ratio and the center of mass velocity of our systems. And we can combine these later on with our periods to ascertain the mass transfer history in our system. And this is independent of the disentangling again. So this is a good measure of our mass ratio. We also get our light ratio by what I said, take the whole disentangling over the range, split it into boxes. For each box, try and shift the templates in a relative flux ratio to each other to get a flux ratio as a function of wavelength, which is the red line that I'm plotting down here. On the x-axis here, we have a wavelength. On the y-axis on the top, we just have the flux. And on the bottom, the flux ratio. And basically what this does is it gives us a further constraint on our SCD fits, because SCD fits there's a degree of degeneracy in there, but by taking spectroscopic temperatures from our disentangling and our spectroscopic flux ratio, we actually make the constraints tighter. And that lets us do some more involved SCD fitting, giving us the radii and the distance to the system. And on our plots here, I'm showing the donor spectrum in pink, the accretor spectrum in blue, as with the other plots. And the solid lines are the results from this work here with the spectroscopic temperatures, whereas the dotted lines are the results from El Badri et al. So we don't actually disagree a meaningful amount with each other, but there's some refinement that can be done here. I've been alluding to assessing the mass transfer history, and the way that we do that is that we get the modern day mass ratio from this TOT core stuff that I've been doing. We get the modern day period by doing orbital fits that Johanna did for me. And we combine that with the equations from Soberman from 1997, which basically lets us model backwards in time how the period evolved with the mass ratio under certain assumptions of mass transfer conservativeness. When I talk about mass transfer conservativeness, we often talk about this beta parameter that basically just quantifies what fraction of mass we lost from the accretor as the mass was being transferred. And I'm not the person to come up with this sort of procedure. Other people started in the past. I want to highlight Julia's work here from 2020. But basically, what we do is we look at our present-day period mass ratio, which I've marked with a black little star as measured by this work, and then we go backwards in time and see how the mass range, how the period changes with mass ratio under these certain assumptions for beta. What we can also do is sort of imply a minimum periods that the system must have had under the assumption that the two stars were detached in the past. And if we do that, subject to the main sequence mass of the donor before mass transfer started, that basically gives us sort of a hard line of we can't have dipped below this line in the past. Period would have been too short and the system wouldn't have been detached. And this lets us actually rule out certain mass transfer scenarios where the mass transfer is not conservative enough because the orbit would have shrunk too much, would have been too small, and therefore certain values of beta are ruled out, subject to the present-day mass ratio and period. Cool, takeaway, what have we learned so far? Basically, the disentangling has confirmed the earlier results that all systems do in fact have a luminous companion. There's not a single SP1 in this sample. And they were all revealed through spectral disentangling, which lends itself really well to these sort of strange systems with strange spectra. They were all very likely formed through mass transfer, as indicated by the rapid rotation of our accretor. The stellar parameters that we found are broadly in agreement with El Badri and Rix. There's some where we agree more or less. I'm happy to talk more about that if you're curious. Mass transfer in all cases must have been fairly conservative, as non-conservative mass transfer would have meant that the system weren't detached in the past. This is also not a new finding. Both Julia and also Thibault, who I think will be talking later this week, have found that like generally we prefer mass transfer to be fairly conservative in these systems. The secondary is rotating in all cases and is rotating rapidly, but it is far subcritical, which implies that either it never spun up to critical in the first place, or that it must have spun down by some very efficient mechanism, much more efficient than what tidal synchronization will allow for us. And with that, I want to just quickly highlight that as of today, you can read about this on the archive, so please go and check out the paper if you're interested, or just come and talk to me, and I'm happy to take any questions.
Thanks. So based on the periods of these binaries, do you have an expectation for like which ones started mass transfer on the main sequence or which ones did like case B, and whether that changes how conservative your mass transfer was?
I haven't actually looked into this, but that's I think a very valuable thing to be doing, yeah.
Yeah, thanks. Very nice work. You didn't state what you assume for the angular momentum loss, but that's essential in your central plot, in how these curves grow. So for the non-conservative mass, there's mass lost from the system. How much angular momentum does it take from the system?
I don't know what Silverman actually assumes in the equations that I put in there.
You can assume anything. What is very common is isotropic re-emission from the
yeah,
accretor.
sorry, yeah.
Yeah. So actually, that's also an assumption that is unclear if that is true. And so the depth of these curves for the light blue ones will change there. And so,
No, this is very. I didn't want to go too deeply into the weeds there, but this is an extremely simplifying assumptions, right? Like the assumption that we're.
Oh, I'm happy with this. This is well done. But there's one piece of physics you need to specify here,
okay.
and that will move.
Your last thing, you had questions at the end, and at the end you have never spun up to critical. Can you expand on that at all?
Yeah, so there's a little bit of stuff in the literature that I think is starting to gain traction again. That's from there's Popham and Pchinsky. I don't remember the years of the publications right now, but there's basically this idea that as the secondary is or the accretor is accreting mass, interactions between the star and the disk allows for angular momentum transport outwards as mass is still being accreted onto the star. So that actually spin up wouldn't be as efficient as we have assumed in like very simple models in the past, because we can sort of drain that angular momentum away as we're doing so. But I haven't actually run the maths on how exactly that would have to happen for this to work. But it seems Sama has many opinions on that one.
Iris, nice work. About the mass transfer efficiency or conservativeness, I know for HR 6819, which is maybe the strip setup for which we have the best mass constraints and orbital constraints so far, Picot et al. Recently published that it's virtually impossible to reproduce even with conservative mass transfer. I know that Thibault and Qian, who you mentioned there, also looked into this. I'm not sure how well they agree. My question is, do you find any systems which are also virtually impossible to reproduce with conservative mass transfer?
So I'm just showing one of the targets here, but there was one of the 6 of them. I don't have the plot for it here with me right now, but it's in the paper, where with the parameters that Karim inferred originally, all of these lines dip below the sort of minimum mass. And even so I find a more conservative mass ratio, but even then you basically expect like 100% fully conservative, and only then could you create that system. Which I think is sort of in line with what you were saying. In these 6, with my results, none of them are like impossible, but it is a little bit suspicious that the mass transfer must have been extremely or hyper extremely conservative, basically.
All right, so let's thank Reese for his talk, and then afterward he has an announcement.
Yeah, I wanted to also use the little chance before we go into the discussion session to advertise the Binary Banter Discord. If you've seen me at a conference again in the last 3 years, you've seen the slide before, presumably. Basically, it's an online community for early career researchers, so anybody who doesn't have a permanent faculty job, PhDs, postdocs, undergrads. We talk to each other about our paper, our work. We have a journal club. We try to help each other with applications. So if you feel like this is something that could be useful to you or your students, please do share around. There's a QR code at the top that lets you fill in a little form that basically just asks, do you like binary stars and do you not have a faculty job? If you answer both of those, feel very welcome in our little group. If you have any questions about it, feel also free to reach out to me in person or on Slack, and I'm happy to provide more information. Thank you.
All right, thanks, Reese. So now we have a discussion section. So like yesterday, we'll have all the people that gave a talk in this session come up.